Hello, thanks everyone for coming back to this hot room. And I like it, you're all now coming together close to the ventilators. So we start with, as I explained this morning, with all the levels, but now we start really, we have two presentations on FHE, where we are, what's state of the art, and the end of the day, we end with post-quantum. But first now, Wouter. Wouter is a senior PhD student with lots of experience already on FHE, also on the application side, all the way to compilers and hardware. The floor is yours.
Yeah, thank you, Ingrid. Welcome everybody to this block of FHE about fully homomorphic encryption. And I will go really into the complete stack, like going from what is FHE, what are we going to do, and most specifically, how do we make it fast and how do we make it more usable. So to get everybody first up to pace, like I'm gonna rapidly go over like what is FHE, what is this fabulous fully homomorphic encryption techniques. And FHE is actually one of the more recent advances in encryption, which enables us to do computations on encrypted data. For instance, it's possible for me to have a number X encrypted already, to have somebody of you determine a number Y and encrypt that as well. Together, we can send now these encryptions of these two numbers to a third party, to a computer, to a cloud server, and this server can now add these two encrypted numbers together and then send us the outcome of this operation can be sent back to the both of us. We can decrypt that, and we can find out that indeed our numbers are just added up together. What now enables us is that all of the heavy lifting of our computations is done on somebody else's computer, on a cloud server, while we be assured that actually our data is being kept private. We can send now our data to servers that we don't trust, that are absolutely not privacy friendly, but with FHE, we are assured that our computations happen by somebody else's, while we're being assured that nobody can actually see what our X or our Y is. FHE is very fabulous, so why don't we have it already? It still has two big bottlenecks, namely latency and usability. FHE is still a factor 1,000 to 10,000 times slower than the according plaintext operation. So you still need to do lots of heavy lifting on your server. The second thing is usability. You need PhD level knowledge of FHE to efficiently program an algorithm within this FHE world. And since there are not so many FHE experts, this is a real problem for getting a wide deployment in companies, in governments. But we've been looking at this problem for the last 10 years mostly. So we have developed hardware to accelerate all of these operations. We are now at the point that our speeds are acceptable for companies, are acceptable for governments. And for the usability standpoint, we have built compilers so that anybody basically can write out a very high-level Python program, very stupid, simple program, give it to the compiler, and the compiler will output the most efficient, most secure equivalent of your input program that you have been giving. But we still have two fields, and that's something that we have been looking into in the past couple of years is, cannot we simply incorporate all of our hardware into our compilers as well, so that we can just combine both of the two worlds and really get the best possible algorithm in FHE put it out. Within FHE, we have two big paradigms. We have the first paradigm, which is the arithmetic style of schemes. And in these type of schemes, you can see that as you give it a vector, and the vector is completely encrypted into a single ciphertext, which makes it very powerful because you can already encrypt 1,000, 2,000, 3,000 elements into a single ciphertext. but it's in a single ciphertext. In the other style of schemes, it is the binary set of schemes where we're going to encrypt an individual bit or very small bit integer. Think 2-bit, 4-bit integer into an individual ciphertext. Both schemes have their advantages and disadvantages. But if we look a little bit closer into it, is our SIMD styles of schemes typically only support polynomial operations. So with that, polynomial operations, additions, subtractions, multiplications, but they do it on the complete vector as a whole. This really has a parallel of the SIMD style of operation that you expect with vector instructions on a CPU, so that you can just add vectors together. The three big algorithms here, or schemes here, are the BFE, BGV scheme. These schemes work on integers, so typically you have an integer vector that is then encrypted into a single ciphertext. And then you have the more recent CKKS scheme, which enables us to do a floating point number or a fixed point number vector and encrypt that into a single ciphertext. Mark will go deeper around these CKKS schemes in his presentation. On the other side of schemes, we have the binary set of schemes, and these enable us to do arbitrary functions. As I said before, they are able to encrypt these individual 2-bit or 4-bit integers, and they can, because of what happens in one of the functions that I will go over in a moment, they can do arbitrary computations. With that, we really think about any possible nonlinear function that you can think about. Think about ReLU, min functions, max functions. They all can happen pretty straightforward in the binary set of schemes. They can also happen in the SIMD styles of schemes, but then computations become more heavy to do. So efficiency-wise, that's roughly not the best solution. The fourth big scheme that is being considered the standards in this FHE is the CGI TFHE schemes, and they encrypt on booleans or on these small bit integers. One thing to note is that within the TFHE scheme, it is also possible to encrypt larger numbers. If you have, for instance, a 64-bit number or a 128-bit number, you can decompose that into a radix representation to just simply convert your 64-bit number into 32-bit 2-bit elements. And then all of these 2-bit elements you can then encrypt into an individual ciphertext. But because of this radix representation that you can use, you can actually encrypt way larger numbers or represent way larger numbers. But now you're just going to use multiple individual ciphertexts to represent one single number. While in the arithmetic type of schemes, you can adapt your security parameters under which they work to accommodate bigger numbers or smaller numbers as you like. Now, FHE has mathematical some properties that are some problems. For instance, all of these schemes are noise-based. What does that happen? Is when we encrypt a value, for instance, our x, inherently the ciphertext will have some noise in it, depicted here with like this very small thermometer. This noise, it's okay that it's in there. You can just encrypt, decrypt your x, you will still come out a certain number. But once we go above the red line, the decryption will actually start to fail. There are some mathematical properties, mathematical reason behind that. I won't go into deep in that. But you must think, if we're going to do operations on multiple of ciphertext, if we want to add our x and our y, the noise will grow linearly as well because of we did an operation. The two noises will basically just be added up and stored inside this ciphertext. The same behavior we can see when we want to multiply two ciphertexts. If we want to multiply our x and our y ciphertext, the noise will grow bigger. And here already, the encryption of here our x times y has already somewhat too high noise to do further operations on it. And that's something that we want to prevent, because in FHE, you don't want to stop in the middle of your algorithm. Oh, my noise is too big, so now I cannot continue. Yeah, that's something that you absolutely don't want. So therefore, we have developed, or there has been developed, an operation which is called bootstrapping. And bootstrapping is basically saying, oh, I have a ciphertext with too high noise, just remove the noise. ID, very nice. But now, how are we going to do that? And because it's FHE, we can do operations on encrypted data. We can also evaluate our decryption algorithm on the encrypted data itself. Let me go on. First thing is, this algorithm we are calling bootstrapping. And bootstrapping basically says, oh, we have here our encryption with very high noise. Oh, we want to output the exact same encryption in the exact same ciphertext, but with lower noise. But now, how are we going to do that? Take a ciphertext encrypted here in a blue key, using a blue key. The first thing that you conceptually can do with bootstrapping is encrypt the ciphertext in another ciphertext using, in this case, a purple key. But now we have a ciphertext containing another ciphertext, but the outpost ciphertext has this lower noise balance. And what we now can do is, in this purple domain, we can now evaluate the decryption algorithm of the blue key. So basically removing this blue border and keeping our value inside. But one thing you don't want to do is just throw this blue key into the purple key's encrypted space. If you just gonna put your blue key in there and you just want to evaluate your decryption, this could lead to side channels. This could lead to actually the leaking of the blue key. But luckily, we work in the homomorphic domain. So one thing we can actually do is, oh, we can encrypt our key inside the purple domain. And if we encrypt our blue key in the purple domain, we can bring it to the purple domain to do the decryption key, but with an encrypted version of our decryption key that we want to use. And this procedure is actually called bootstrapping, where you end up with the exact same encryption, but with way lower noise than in the beginning. Very cool technique, but this is considered one of the most needed the most resources to calculate these types of algorithms. This has been developed 20 years ago, so there has been a lot of new things happening. And one of the cool things is that, for instance, in the TFHE scheme, you can do an additional step during this bootstrapping operation. Because of mathematical properties, the way that TFHE is built up, how bootstrapping is done, you can actually do an additional step of doing a table lookup during this bootstrapping operation. This is also the core why TFHE can do completely arbitrary functions. So what can this programmable bootstrapping now actually do is it can do a table lookup during its bootstrapping procedure, meaning that if we, for instance, first going to build up a table with a certain amount of indexes, 0, 1, 2, 3, 4, 5, and then our function that we want to evaluate. Now, just for an example, I have put here this table, but anybody can decide what kind of table that you want to put there. What now TFHE can do is, during its bootstrapping operation, it can take completely anonymous, like the execution of this bootstrap operation don't know any of these contents. It can take the content of the number and pick up, use this as an index for our table lookup, so that we can convert our 3 here into a 7. Doing this is completely free. If you are going to do the programmable bootstrap, you're going to do this table evaluation anyhow. So you don't need to compute additional resources. You can just take this here. And that's the way why we want to, or how TFHE can do completely arbitrary programs without any polynomial functions. So that was it for the FHE introduction. But now, how are we going to accelerate FHE on what kind of platforms, and so on. If we take our classical compute model, if we take our CPU that everybody uses day to day, it will look something like this, where we have a big main memory, where we have an executing part of the chip, and basically what will happen is you will write here a software stack. The software stack will go to the control unit. The control unit will read out what your software program wants to do, and for instance, one of the first things that during a computation you will always do is first you will take some memory, put it into the compute unit, and then on the next elements, the next parts of your program, you will do some operations on this data that you just have fetched from memory. When your computation is done, you put it back into the main memory. One of the things is that these compute units are very generic, so they can do basically all of the operations that you want to do because they have a dedicated addition, a dedicated multiplication, an equal operations, a greater than operations. It's all there in the chip because it's meant to be made generic as possible for doing any possible computation or algorithm that you want to do. So, very cool that it's so generic, but one of the problems that we have is that, yeah, you can already see it, right? You're constantly calling elements from your main memory to your compute unit and going back and forward constantly. Yeah, this introduces an overhead that you want to prevent and you can prevent when you are going to build your own chip. If we now take a look at a high-level concept of one of the chips, is that we now here, for instance, in an FPGA, this is a type of compute platform, it is now possible to determine how many compute elements that you're going to put and where are you going to put them. The same thing with your memory. So now in an FPGA, it is possible to have like this very big memory storage in front of your computation, retrieve all of the memory elements that you want to use, and then put it in a compute pipeline, in a complete compute stage of already computations. If you now want to do first thing is do some form of MAC operation on it, so do first this multiplication elements and then add them all together. It is all possible to do this complete operation without going back and forth between your main memory. It is possible to have dedicated multiplication operations, dedicated addition operations on your chip that will do these type of pipelines. So now you can just take in your elements, compute them completely along the way, do some post-processing on them, and then put them only back at the end here in a separated memory. It is now possible to, for instance, already have two types of memory locations, so that you don't need to go and back from your main memory. And as well, it is possible for each and the individual arithmetic operations can be placed dedicated on these type of chips. This is completely different as in a CPU, because in a CPU you only have one of these, for instance, one of these additions, one of these multiplications. So if you want to already do multiple multiplications after each other, it must all go through this same hardware block. While in an FPGA or in another type of chips, yeah, if you want to do 3 multiplications at the same time, you just put 3 multipliers next to each other and you use them in parallel. This is one of the great benefits of designing your own hardware, is because you now can write out your complete algorithm that you want to do with all of the operations that you want to do, and define for each of these operations that you want to do a piece of the hardware to actually do this operation. But now, how does the hardware landscape look a bit like? Is at the left here, we have what everybody knows. It's a CPU, it's in your smartphones, it's in your laptops. It's quite low on performance and energy efficiency, but very good at programmability. Everybody can write a program, and that program will be executed on your CPU. Going a little bit to the left, we got like the graphic cards. Most of you will also know that. Graphic cards already contain more of these compute elements, are more streamlined compute elements. On the left, we have here an FPGA. An FPGA is a reprogrammable chip. I've brought one with me. This is basically just a card that you put in your CPU. It's here, this big silver block is a reprogrammable chip. So we can write out a hardware definition, we can put it on the chip. Tomorrow we can put another hardware definition on it, and we can just continue. There is also another additional class, which is called the ASICs, and the ASICs is when we're going to define a very specific chip, which only will do the algorithm that we put on there. This is typically done, we want to do an algorithm, we're going to put it in an ASIC chip, we're going to make a hardware design, we're going to send that to a chip factory, and that will produce an individual hard-coded chip for doing our algorithm that we have defined. The benefits, of course, for this ASIC is that in this ASIC, we can define where all of the memories are, where all of the compute elements are, which compute elements can talk to which memories and which other compute elements. Making it very energy efficient, making it a very high performance. But because we're going to define everything, we're going to give everything a very fixed place, it's not really reprogrammable, because very typically we want to do 1 or 2 or 3 operations, put that on a dedicated chip, let that chip be made, and we can only do these operations with it. Development costs already are also pretty high, because it is not so easy to design one of these ASICs. It takes a lot of engineering costs. The actual making of the chip as well is quite expensive, but you win in energy and performance. FPGAs, you can just reprogram. So performance-wise, it's very good. Energy efficient-wise, also pretty good. You can reprogram them, so that's also not a problem. But you see that if you want to have the same hardware design, you still can make it a factor roughly 10x better by just going from your hardware design on FPGA to an ASIC. Ballpark numbers. GPU, you're just going to buy them, put software on them, and it can run as well. But now to give you some more insights in, you got a chip, how are you going to put a hardware on this chip, like how does this FPGA work? Is one thing is we first must look at our logical gates. If we want to do an operation, if we want to execute an algorithm, we can start with the very beginning of logical gate, an AND gate, an OR gate, a XOR gate, and just define them as, it has 2 inputs, going over all of the inputs, and we have this table defined. This is called the truth table for this logical gate. Probably most of you will know that. But now, we do not simply want to put all of these tables on our chip. We first want to define the same concept, but now in the electronic world, not in the encrypted world, is using also a LUT, is also a table lookup, where our addresses just go over our complete space that we want to represent. And if we now want to put our AND gate into a lookup table, we just take out what are all of the possible outputs, put them into this lookup table. And this is now exactly what an FPGA will do. Is it first will go over your input hardware description. It will convert this into these type of lookup tables and put like the lookup table definition of your complete program on this FPGA. Inside an FPGA is considered at a high level of these configurable logic blocks. And a configurable logic blocks consists of a LUT, which is called basically, you have like a 4-bit input, 1-bit output, together with a flip-flop. A flip-flop is a small memory element to just store the output of your LUT. An FPGA consists of 10, 100, 1 million times these CLB blocks, and all of these CLB blocks are interconnected to each other. So the output of your LUT is the input of a next LUT. And with that, you can just design a hardware, give that to these tools to actually program your FPGA, and they will convert your input hardware description into the LUT definition of your algorithm that you have defined. And then you can just load it on these type of cards. It can actually be executed, and it can be pretty performant as well. So one of the designs that I want to go over together with you is called FPT. This is an accelerator for TFHE bootstrapping, done by colleagues of mine roughly 5 years ago. And what FPT accelerates is if we want to evaluate now an encrypted algorithm considers of these Boolean gates. So think about that this is actually a graph that we want to evaluate in the encrypted domain. We now want to accelerate these bootstrap operations as you would like. Because what we have seen is that if you have an algorithm that you want to evaluate using these types of Boolean gates, it is roughly always considering about 80% of the evaluation of your algorithm considers of bootstrapping operations. We have a second operation, which is called key switching. But when we saw these results, one of the very obvious things is, if 80% of the time you're doing bootstrapping, you just put bootstrapping on a chip to accelerate your complete algorithm. So again, we want to evaluate these gates in the encrypted domain, not actually put it on electronics or on hardware. And that leads to actually the FPT design, which only accelerates this bootstrapping for gates. FPT has been developed with the idea of a streaming design in mind. And with the streaming design, you can think about that when you want to program an accelerator, you basically will build all of these types of compute regions that does a certain part of the algorithm that you want to implement on your hardware. For instance, what can you think about one of these compute islands is here, like one of these white boxes is doing an FFT. And during the bootstrapping algorithm of TFHE, you want to do a lot of forward entities, do some pointwise multiplications, and then do some inverse entities at the end. So what the streaming design now has to take in mind is that if we have here this compute part that does our forward entities, it will just send them together to the next stage. But one of the things that you can think about is, okay, we put here in a ciphertext. It is transformed into the Fourier domain, and it then goes to the next stage of the pointwise multiplication. Yeah, one thing is, once you're done doing this forward transformations and going to the pointwise multiplications, already a new ciphertext can use these compute elements because it just goes to the next part of your accelerator. That's way it is possible that actually this design works on a batch of 12 ciphertexts. So basically, once one ciphertext has completed the first part of the algorithm and goes to the second part, another ciphertext can already start with, again, the first part of the algorithm, leading that this design is actually fully compute-bounded, meaning that we cannot make this type of accelerator any faster because our algorithm, like all of our hardware that we have put on the chip, has a utilization of almost 100%. What we typically see with other accelerators is that because of the sizes of FHE, of our FHE ciphertexts, the sizes are up to kilobytes, megabytes, is that we often see that other accelerators are memory bottlenecked. So that our compute units must actually wait till we have fetched some ciphertext or some key material from another side of the chip that has been stored in memory. And that just, our compute parts are there just waiting idle till they actually have enough material to be computed on. Yeah, was actually a fabulous design that completely could prevent this memory bottlenecks and have a very, very high utilization. For any details about the accelerator, it is actually pretty genius. I can point you to the paper of our colleagues to get some more insights in what happens. One of the things that is actually still quite funny to see is that FPT remains relevant. For instance, if we take a paper published a couple of months ago, which has been done an ASIC design for the exact same algorithm, we can see that the chip is called Yatta. The chip works 2 times faster. It has a clock frequency of 400 instead of 200 megahertz. So the compute elements can, or the basic elements can work 2 times faster. Yeah, if it works 2 times faster, we can somewhat expect that our latency, so the complete time to calculate, has also a drop of 2 times. That's very nice. But one of the things, because of this very compute-bounded pipeline, is that actually the throughput of FPT is very high. Roughly, you can see that we have like 28 ciphertext processing per millisecond, while if we check at our ASIC, yeah, you only have 3 ciphertexts per milliseconds that you're going to compute. One thing, of course, that you can take into account as well is that the power consumption of your ASIC is also way more factors lower. But still, on the throughput front, till today, FPT remains one of the best hardware accelerators that there is for doing TFHE bootstrapping on Boolean gates. Okay, now that I've been talked to hardware, I have given you some insights in that, as sadly as people would like, hardware accelerators are not just a plug-in and replacement operation. For instance, for FPT that we have discussed, it works best if we have multiple sizes, or if we have batch sizes of 12 ciphertexts. But that already means that our programmer must be able to program 12 ciphertexts at the same time. Again, raising the bar a bit, making our FHE programming, again, a bit harder, because now our programmer must find these 12 ciphertexts. One thing is also memory movement. Is if we have our FPGA and our ciphertexts originate from the CPU, we constantly are going to transfer from our CPU memory to our FPGA and back to our CPU memory. CPU will do some operations, we'll send it back to our FPGA. FPGA will send it back to CPU, and so on and so forth. This is also something that we want to prevent because the transfer times from CPU memory to FPGA memory is also non-negligible. So if we can find a program that prevents us from doing some of these transfer operations, yeah, that would be very nice. But that are also problems that you can find with our compilers. And if we look at a very typical compiler pipeline, it looks like this. Most of you will probably notice if, you're going to write C or C++ code, this is first translated in some form of abstract syntax tree, basically translating your code into a form that a compiler just can understand. It doesn't have done any optimization. It just converted to a form that it can reason about. That is then ported to the LLVM IR, and within this LLVM IR, we will do the first optimizations. We will try to find, is it actually logical what you're doing here? Can we just not find any optimizations? Can we remove some variables that you declared but didn't use at all? This is all quite high level. This will then be converted into machine IR, and within this machine IR, machine intermediate representation, we can already start to reason about what kind of platform are we running at. Are we running at a laptop CPU, which uses 64-bit registers? Are we running on a server CPU which has 64 cores, 64-bit registers? Are we running at these very small IoT devices, these microcontrollers, which uses 16-bit operations, maybe only 1 or 2 cores? Yeah, this is all what we're going to reason about in this machine IR. And then it will actually eventually output assembly, which is then code that can be run by these hardwares. But one thing that we already see is that these pipelines are very much ported already to CPUs. They already at the LLVM level, so once they basically start doing optimizations, all of these optimizations are focused towards you're going to run on a CPU-like architecture. And with a CPU-like architecture, I mean, oh, you have a main memory, you have a compute unit, these two constantly go back and forward. But within that model, already your LLVM optimizations are taking place. And that's one of the things that some other guys have thought about as well. That LLVM already has been very specific towards the CPU platform. And that's why the people of LLVM actually started a project a couple of times ago, which is called MLIR, which is the multi-level intermediate representation. Basically, MLIR is a tool set of, is a library to define your own compiler. With that, they want to have a generic approach to a compilation pipeline as possible. But already MLIR gives a lot of existing optimizations that are 100% platform independent. One thing is, for instance, common sub-expression elimination. If you want to do B times D plus G, B times D plus E, yeah, you don't want to do P times D 2 times. What you want to do is put that into a separate temporary variable, compute B times D 1 time, and then the outcome of that variable, do it plus G, do it plus E, and then we can go on. Yeah, these are algorithmic optimizations. These are not considered to be on the hardware at all. Another thing is that code elimination. If you have a programmer that likes to write a lot of verbose codes, but not always the most efficient things, a compiler can find out if it has declared variables that you just want to remove. Affine looped optimizations. If you are going to write code which has nested loops, these affine loop optimizations can already determine, oh, inside your inner body of your loop, thus you actually iterate over your loop counter. If you're going to do, for instance, every loop a setting of 0 of a specific element, but that specific element is not defined by your loop counter, yeah, you can just host it out over your loops, put it out of your loop definitions. Then you don't need to do, every time you need to do a loop, these types of operations that are that are not essential for your loop. It is actually quite being a popular environment. One of the newest Fortran compilers has been designed in MLIR. Another program is Circuit. Circuit is actually a hardware compiler. That it is possible for people to have like a high-level definition in Python, in Scala, something like that. Give it to the compiler, and then the compiler will determine your hardware. It will determine a hardware-specific output that actually people can put on an FPGA as well. Because we have a new rise of quantum computers as well, quantum computers have a different paradigm to compute in, have a different hardware architecture. We can use MLIR for those parts as well. And of course, we have the AI hype that everybody has been aware of. A lot of these AI new architectural computations, they all want to invent new ways of doing these AI optimizations and AI algorithms. Yeah, one of the things is you can invent a new chip to do this AI algorithms way more easy to do, but the thing is still, if you have a high-level model, that model still needs to be mapped to your new architecture that you have built. So the mapping of high-level code into these new compute platforms is also being done with MLIR in mind as well. But now, how does a very typical MLIR pipeline looks like? Is within MLIR, we are going to use a lot of dialects. Each of these dialects is considered to be an intermediate representation at a certain behavior, at a certain level. Meaning that if, for instance, take the case of our hardware, we are going to put in a very high-level description, but then we first want to do some parts of algorithmic optimizations. These algorithmic optimizations can be considered into a dialect 1. This dialect 1, at a high-level definition, is then lowered into a next dialect with a lower level of abstraction, so coming closer and closer to our actually backend that we want to produce. But already this dialect 2 has a specific set of behaviors, has a specific set of playing rules, but we can exploit these playing rules at that certain behavior to make it more efficient. And then what I basically want to tell you is that each of the dialects has another level of abstraction, and going from one dialect to another dialect will lower your level of abstraction and will make it more oriented towards our backend. To make it now, that was quite abstract, to make it all more real, one of the compilers that has been built in our past couple of times is the homomorphic encryption intermediate representation. This is an open source MLIR compiler which is focused towards FHE. And the goal of this compiler is really to be like that anybody can write a C program, a Python program, that you can import high-level machine learning models with TensorFlow or Torch, give that to the compiler, and the compiler will produce library called code or code directly for hardware accelerators, or going for LLVM already, and then once we're in the LLVM world, we can use the Clang compiler going down to CPU-compiled code as well. But now, what you can actually see is that all of these white boxes individually are these types of dialects. So at the top, we have this standard MLIR dialect, and these are the dialects that we get from the MLIR framework. And these are all just general tools, general dialects to work with. For instance, we have the ARID dialect, and in the ARID dialect, we will just do all of the basic mathematical operations. Additions, multiplications, extensions from, for instance, from integers from 8-bit to integers from 16-bit, min operations, mac operations, all of our basic mathematical functions are situated inside the ARID dialect. Together with the ARID dialect, we also have, for instance, the tensor dialect. The tensor dialect gives us a possibility to not work on individual elements, but on n-dimensional tensors. Meaning that if we combine the two dialects, it is possible to define a 4-dimensional tensor addition. All possible to represent in this MLIR dialect. But now, how does a very typical compilation pipeline look? Is we define a high-level algorithm in Python. We first convert it into the MLIR dialect, so in a representation of MLIR that the framework can reason about. And then one of the first things, for instance, that we can do is go to the secret dialect. And the secret dialect is a dialect specific to hair. And within this dialect, we're just going to determine, okay, if you start with, if you want to do a matrix vector multiplication, for instance, but your vector is considered secret, your matrix is considered plain text, you can just simply do plain text ciphertext operations, but that will produce a ciphertext as well. But we must denote that throughout our complete program if anything that touches a ciphertext will produce a ciphertext as well. So we now can denote all of our intermediate values using the secret dialect to what parts are going to be secret, what parts are not going to be secret. Once we go to the secret dialect, we can go to one step lower, and we can start to choose which kind of FHE scheme that we want to use. Do we want to use BGV, CKKS, or maybe TFHE? But back again, when we have converted our secret model into one of these BGV, CKKS types of schemes, each of these schemes have a different set of playing rules. They also have a different set of FHE operations. We can already, because we have defined a BGV dialect, we can now do BGV-specific optimizations and operations on this intermediate representation. Once we have found the best possible BGV implementation of our scheme, we can now go one step lower. A lot of these schemes are built upon polynomial operations on modular arithmetics. We can now just simply convert all of our BGV operations into these very basic mathematical properties. So leaving the FHE space definition, but still having now the scheme implemented on these types of levels. And once we have our program defined at the mathematically lowest possible level, we could go to a library to actually implement all of these operations, or we could directly go to an LLVM dialect that will now just implement these polynomial multiplications or additions, or go to a hardware dialect to do so. One of the nice things is, for instance, last year colleagues have developed a new scheme, namely GBFE. Because of MLIR and because of the compiler how the compiler has been built, we can just simply add GBFE at this level. And because it uses also this SIMD behavior, yeah, we can just use all of the other operations that are already in there. We can just simply use them. We just need to connect them together. Other thing as well, if, for instance, a new hardware vendor comes to the project and say, oh, nice, I have completely designed a new hardware dialect, but it works on complete BGV ciphertext, and I just want this BGV definition. Okay, once we get like this BGV schematic, yeah, from that point on, we can just export our program, give that to this hardware developer, and they can now just convert the algorithm into a system that works for their chip. Because of MLIR, all of our works and how everything is relying on each other, we could just define it ourselves. If you want to change, if you want to remove blocks, one of our very cool nightmares is if tomorrow one of the schemes is out of style, or is being considered broken, yeah, we just remove it, replace it with another scheme, and we can go working on that. Because of the extensibility of this system, it's very cool to work on. But now, what is all in there? We have a Python frontend, so people can just write Python code. It will output. I will go over it because quickly go over it. We have scheme supports. Today, mostly all of these schemes are being implemented in libraries. So what we typically do is from the BFE, CKKS, BGV definition, we just export code that works with these libraries. We have polynomial approximation as well. For the BGV CKKS style branch, we cannot do any nonlinear functions. Yeah, we can just add the polynomial approximation step in there. That will convert these nonlinear functions into operations that can actually be executed with our schemes. We have a noise model step in there as well. Because it's FHE, all of our program is completely statically defined. So we can also do a noise estimation. For instance, here you have two input ciphertexts. They have already a certain noise bound. You want to do a multiplication. Okay, the output noise bound is this. And go on and so forth. This also gives us the possibility to add or insert bootstrap operations only at the points in our algorithms where it is required to do. We can all do this in here. Another thing is the ciphertext packing framework. because I said to you that once we encrypt the vector into this SIMD world of arithmetic style things, once it's in there, it becomes very hard to select data from the vector or to just simply move the data in that vector around. One thing that we want to know is if we need to encrypt our vector in a certain way to prevent all of these fetching and maintaining operations, the compiler already can figure it out. We can do all of that. But now, quickly go over it. We have developed a complete CGI pipeline, which go from a high-level TensorFlow model completely down to the hardware accelerator. And one of the first things that we can do is actually target the FPT backend. How are we going to do that? Because we have a high-level TensorFlow model, you can think really about this as a one-liner definition, like first layer, one line, activation function, one line. First things that we're going to do, put that in here, and here will now convert this into a Verilog definition of our TensorFlow. Already this Verilog definition is the arithmetic version of our input program, but is already somewhat optimized. This Verilog definition we can put into Yosys. Yosys is a hardware synthesizer tool, and this will convert our arithmetic model, so our loops and our multiplications, our addition, it will convert that into a Boolean definition of our program. Once we got the Boolean version of our program, the next thing that we want to do is look for these batch sizes, is look for what kind of operations can we parallelize actually. This parallelization happens again in here, and once we get that parallelization, we're going to put out Rust code, which can then be run on our FPGA. Now, how are we going to do that? How are we going to find that parallelism? Actually, quite straightforward. We have here our outputted algorithm that comes from the Yosys tool, and we're just going to convert that into a graph and do a level sorting on that graph. Meaning that if we have level sorted the graph, each operation that is sorted in a specific level will be independent from each other. Meaning that at a certain level, we can just say, oh, at level 0, what we found here at level 1, very typically, you don't find parallelism at that point yet. So you're just going to put that into separate operations. One thing is, oh, at the next level, at level 2, we already found 2 operations that we can do actually in parallel. So we converge those 2 operations into a single operation, into a single call, but now with 2 ciphertexts. And we can send these 2 ciphertexts already to the accelerator, increasing our usability. And we can go on, till at the end of the program, very typically, you find 10 call to the accelerator with 9 elements, so having a better utilization. And then that can be put on our FPGA. The second and the third pipeline that can work is not by telling to Yosys, oh, you now need to convert to Booleans, but now you can convert to a LUT definition. And basically finding the equivalence of our arithmetic model into a LUT definition. We have looked at 2 possible LUTs, a LUT3 and a LUT4. What's in the name? 3 1-bit inputs, 4 1-bit inputs, 1-bit output, 1-bit output. So that users can just basically now generate using this LUT definition. The fourth backend that we have is actually don't go to this synthesization domains at all, and just use the hair compiler and let everything be in the arithmetic domain. For this, we also target a different backend platform. The authors of FPT have extended their platform to the integer domain, but also they have implemented it into the high-level API of their Belfort implementation as well. And how can you look at that? Very easy. How does this high-level API look? Very easy. Just encrypt an A, encrypt a B, and add them together. It's simple as that. So what we basically do with the compiler is just make the best possible arithmetic model and then export that to the library and let the library call at it. So to give you a small overview, if we have our high-level model, we will do arithmetization anyhow, but we can put it in Verilog into UOSIS, and then we can determine, oh, are we going to target the Boolean API? Are we going to target the LUT3, LUT4 API? The Boolean API is executed on FPT. The LUT3, LUT4, and HL API will be executed on the Belfort extended version of it all. But now to give you an idea about how fast is it? If, for instance, if we consider a very small MNIST network with 2 bits quantized weights, so input is very small, is 2 bits. All of the weights that we want to compute are 2 bits, are very small. We can see that if we run this Boolean network, so going through UOSIS, going from our arithmetic to our Boolean model, sequentially computing all of the gates after each other is roughly an hour. Doing that already parallel on the CPU, it's 4 minutes. But now the crazy thing is, we can already execute all of this sequential model on 4 FPGAs at the same time. Because for the compiler, it doesn't matter if we have 1 compute platform or 4 compute platforms that it needs to send. If it has the parallelization, it will just send them throughout everything, leading to an efficiency of 270x speedup. One thing that I do like to denote, which is actually very funny, is that this very small MNIST model already takes 14 hours by hair to compile it, which means converting the high-level model into the arithmetic model, let UOSIS convert this arithmetic model into the Boolean model, and then finding the parallelization of this arithmetic model into the Rust code. And now the funny thing is actually that the Rust code that is produced still takes 7 hours to compile within Rust. That's mostly because Rust has the compilation passes of Rust are quite secure, and they want to keep a security of the whole program as a whole. But if you are like me and you output a program with 200,000 lines and 200,000 calls to certain APIs, Rust struggles to represent that big of a program with all of these individual lines. To give you an idea of all of the others, yeah, one of your takeaway messages is basically, if you want to do, if you compare all of our 4 pipelines next to each other, your Boolean will get you the best results. This will get you around the 11 seconds that are just been showed, but you need to take you need to think about roughly 15 hours of compute time. The HL pipeline is the second best, which is basically done in a couple of minutes, so pretty fast, but it is a magnitude roughly 10 slower than the Boolean pipeline. For full comparing, we have the LUT3 and the LUT4 elements in there as well. It also have a high compile time, because it needs to go through UOSIS, it needs to go to convert this LUT3, LUT4 elements, and as well, it is not, they're pretty slow in the actual evaluation of stuff. So that's basically my talk. One thing is that the 2 takeaway messages that I would like to give to you is we're going to need accelerators to actually enable FHE for a wide audience, but there we'll go Mark a little bit deeper in them. But one thing is we also need compilers, because people can build as fancy as accelerators as they want to. If you don't have people to actually, or programs to make efficient programs for them to increase their utilization, then your accelerator is just more than a piece of nice hardware. So, thank you everybody.